Okay, so today we'll continue on with some of these addition reactions, and we'll look at the synthesis of higher order amines using reductive amination. And then we're going to look at some unique type of carbonyl additions. And then we'll end with a couple reactions that bring us up in oxidation state to functional groups like carboxylic acids, esters, amides. And then we'll continue on with that through the rest of this module, looking at those functional group transformations. So our first reaction that we're going to look at is called reductive amination. And so we're going to utilize the condensation of an amine with a carbonyl, and then we're going to reduce that imine or enamine bond that we've formed. And so that basically allows us to go up in the classification of the amine. On this slide, what I've just drawn in there in red is how that imine is formed. And so when we look at that imine, we see an oxidation state 2. We know that that can come from the ketone being condensed with a primary amine. So we start with a primary amine, and now we want to reduce the CN double bond. And the conditions to do that use this reagent called sodium cyanoborohydride. We've seen sodium borohydride before to reduce carbonyl groups down to alcohols. This one is a little bit different in that the cyanide is essentially weakening the power of the borohydride even more. And what you'll notice under these conditions, we have hydride, but then we also have an acid, trifluoroacetic acid. So that should seem a little bit of a red flag to you because hydride is H minus, acid is H plus. How can these two things be in the same reaction without first reacting with one another to form H2? So they have opposite reactivities. So essentially they're working in concert to reduce that CN double bond. And so that's called reductive amination. And on the next slide, I'll show you why we need the acid in there and why it doesn't react with the hydride right away. So pH is just the abbreviation for a phenyl ring. So what happens first and why the acid is in there is that the imine will be protonated. So the imine lone pair on nitrogen is a base. It abstracts a hydrogen from the trifluoroacetic acid. And then we can balance off the plus and minus charges like that. So a protonated imine is called an iminium ion. So we have one hydrogen of the two that we need for the reduction. So the nitrogen's been protonated, and now the sodium cyanohydride will come along as the reducing agent. So because nitrogen wants its lone pair back, hydride will add to the carbon. The double bond electrons go onto nitrogen. That species ends up neutral, and then we balance off the sodium with the trifluoroacetate. So imine double bonds will always use that combo of reagents, whereas with carbonyls, you just need the sodium borohydride. And so overall, what we've ended up with now is a secondary amine. So whatever you start with, it's going to go up one classification. Any questions? So what we'll look at on the next couple slides is how is this generalized? So given any amine, what are the ways that we can dissect it to make it? And this is similar to what we saw with any sort of alcohol. There are three ways you can make an alcohol. So we'll look at the strategy with amines, where we're focusing on now what is bonded to the nitrogen. So here are the strategies, and we'll show a specific one coming up. So we're either starting with an aldehyde or a ketone. These are the different classes of amines that you can use, either ammonia itself, a primary or a secondary amine. The condensation product is listed here. So remember, ammonia and primary amines give imines. Secondary amines give enamines. And then what happens from that class once you do the reductive amination? So you'll notice it goes up. So ammonia will become a primary amine. Primary amine becomes secondary. A secondary becomes tertiary. So given any amine, you're basically looking at the CN bonds and dissecting it between a carbonyl component and an amine. So of this compound shown, N-ethyl, N-methyl cyclopentane amine, it's a tertiary amine. And so we're focusing on the nitrogen. We can see we have 1, 2, 3 different carbon groups bonded to it. So that could be one way to dissect it. That could be a second. And this would be the third. So what we'll do on the next slide is just draw out those three different scenarios of what is the carbonyl component and then what is the amine component. So if we wanted to dissect there, the part that contains the nitrogen is going to be the amine component. The other part has to come from a carbonyl. So in this case, we would start with a secondary amine, and then this would start from an aldehyde, because we have from that carbon, and then H. So a secondary amine condensed with that aldehyde, followed by the reductive amination, would be one strategy. The second strategy now with the blue line is going to use a different secondary amine coming from a one carbon aldehyde, so formaldehyde. Now our third strategy still coming from a secondary amine, but now the carbonyl component, because that carbon is bonded to two other carbons, is a ketone. So there's three ways you can do it, and practically speaking, which way would be the best depends on what are the costs of each of these, and then what are any safety concerns in handling them. For example, like this one carbon aldehyde, formaldehyde, can be a real pain in the butt to deal with. So that might not be the best way to go about it. The 2-carbon acetaldehyde, that can also have purity issues with how it's bought. So this ketone might be the best strategy to start with there. And then you have this methyl ethylamine, so that would be probably pretty cheap to buy in terms of dollars per gram. So in the lab, you're considering those factors. What is the cheapest way to make something? But then also, do there need to be any special handling precautions for these things? So formaldehyde itself is a gas. This acetaldehyde, I think, is low boiling, so that can be kind of tough to measure out. If it's super volatile, you don't want to be smelling it. You don't want to be losing it. So the take-home message is this: given your target amine, there's 3 ways you can do it. And then any amine that you start with, again, since these are all secondary, that should be tertiary there. No, what am I doing? That was route 2. The amine itself is tertiary. So whatever your target is, you're starting with a class lower of amine. Any questions? So as we progress through this module, we're going to see another way that we can make amines, but we have to learn how to make oxidation state 3 functional groups first. So before we get all to that, maybe see if you can predict the product of this reaction. So A is the correct answer. So we're starting with a primary amine. So the product has to be secondary. Under reductive amination, we're forming an amine. So B is out because that's an amide. C is an imine, and we know it's the product is going to be an amine, not an imine. And D is just some nonsense. How do we figure out that it is A? So in this reaction, the amine and the carbonyl are tethered together through this carbon backbone. So a strategy to use is to number. So I'll start with nitrogen 1. So that primary amine has to condense onto the carbonyl. And when it does that, it's going to form a 6-membered ring. That species C, which is the imine, gets protonated, and then that gets reduced. So anytime you have your nucleophile and electrophile within the same molecule, you'll want to number the atoms between them so that you know what size ring is going to form. So now we're going to move on to some different types of addition reactions. And again, these are only reactions that will take place at aldehydes or ketones. The first one is called the Wittig reaction. And so in 1979, Wittig shared the Nobel Prize with Brown for chemistry related to phosphorus and boron. So you'll remember we learned hydroboration oxidation in organic 1, and that dealt with the chemistry of boron, so boranes. So Wittig studied phosphorus, and so we're going to learn how to make a Wittig reagent and then take that reagent and react it with an aldehyde or a ketone. The first reaction that's shown here is the formation of a phosphonium salt. So on our periodic table, we see phosphorus is right below nitrogen. So 3 bonds, 1 lone pair. So that's the reactivity. So that lone pair in this sense is going to be nucleophilic. The most common phosphorus reagent is triphenylphosphine. So we see the 3 sigma bonds, there's the lone pair. So the phosphorus is going to be the nucleophile. We're going to react that with an electrophile. So bromomethane. And this mechanism is SN2. So nucleophile displacing the electrophile. And now what we end up with is a salt. Phosphorus is now plus, bromide is minus. Because this is SN2, we will want the electrophile to be methyl, primary, or secondary. Now, what's special about this salt that carbon is sp3 hybridized, and normally the pKa of those it's a pretty weak acid. But we can treat it with a base that will deprotonate it. And when it does that, it forms a new type of intermediate that has a negative and a positive charge right next to one another. So the organic chemistry term for that is called an ylide. In biochemistry, it's called a Zwitter ion. It all depends on the separation of those charges. So here is our salt, our bromide salt. And I'm gonna take this methyl group and I'm gonna expand out those hydrogens. So there's the 3 hydrogens. And then we're gonna treat that with a really strong base, N-butyl lithium. So that's a carbon anion. So it's a really strong base. It's going to deprotonate a CH bond to that methyl group. So that's an acid-base reaction. The electrons from that CH bond then end up on carbon. So the carbon's minus. The phosphorus is still plus. The other stuff that's formed is butane. So that's a gas which comes out of solution. And then we can balance the inorganic stuff with lithium bromide. This reagent here is I'm going to say bifunctional in the sense that you have a negatively charged carbon, so nucleophilic, and then you have this phosphorus, which is plus, electrophilic. Because those charges are right next to each other, this is called an ylide. So the carbon's nucleophilic. And since we're in the module of adding nucleophiles to aldehydes or ketones, that's what we're going to do next, is add that carbon to the carbonyl carbon. So the Wittig reaction, there's your ylid. Here's a ketone. It does what's called a metathesis. The carbonyl becomes an alkene. So I'll highlight in blue. So see this CH2 group? It becomes the CH2 group here. See the oxygen atom, where does it end up? That oxygen ends up bonded to the phosphorus in this byproduct called triphenylphosphine oxide. The driving force for that is the formation of that PO bond, which is plus 544 kilojoules per mole. So later on in this semester, we'll see why phosphorus-oxygen bonds are important in nature, because we see them in DNA. That's how the carbohydrates are linked to one another through PO bonds. So this reaction produces a really strong bond in a byproduct, but overall the organic thing that we're after is an alkene. So any aldehyde or ketone, when reacted with the appropriate Wittig reagent, will form an alkene. So as a preview of the next slide here, so we know that carbonyl is delta minus, delta plus. Strong negative carbon is attracted to delta plus, so that's an addition. And then the metathesis happens. How does that other bond to oxygen break? How does phosphorus get the oxygen? And how do we form the double bond? I'm just going to highlight that in blue. So we see that it ends up there. And really what we're aiming to do is just generalize this for any group that's in blue. The mechanism for this can get pretty complicated, and I'm just going to show you a stepwise thing so you understand the overall reactivity. So we get a nucleophilic addition, we break that pi bond. Oxygen becomes negative. And so from here, this is the metathesis step. I'll show it stepwise rather than putting too many arrows in here. You have a negative, you have a positive. In the stepwise fashion, we're just going to form a bond between them. Notice when that happens, neither the oxygen nor the phosphorus no longer have charges. That might seem a little weird because if you look at how many things are bonded to phosphorus now, it's 5. And because phosphorus is in this third period, it can expand past an octet. So it can accommodate more than 4 substituents. So how do we unravel this? We can have that bond come down. That forms the CC pi bond. We can have that bond break. And then oxygen gets a lone pair. And then the result of that, the O and the P end back up with charges, and that's the triphenylphosphine oxide. So that was pretty revolutionary at the time, a way to take carbonyls to alkenes. It's been widely studied over the past couple decades, but nowadays it's generally recognized as kind of a reaction of last resort, because if you look at this byproduct, you have a stable phosphorus-oxygen bond. So this thing is unreactive, and if you add up all of the elements present in the molecular formula, it's got quite a bit of molecular weight to it. In terms of the economy of the reaction, you have this byproduct with a big molecular weight. It's not very reactive. You can't do much with it other than to separate it out as a byproduct. So the weight of that compared to what you're trying to make is a big difference, and that's called atom economy. And through synthesis, you basically want to use reagents where everything in both starting materials is incorporated into the product. You don't want to generate a lot of waste, because waste is a cost and it reduces profit. So with this, remember, any aldehyde or ketone, this group in blue, as long as you can make the Wittig reagent, can be anything. So when we look at this starting ketone, we want to transform it into this alkene. So notice what I highlight in red. So there's oxidation state 2. So there's the marker for that carbon. So in blue, what did we add? So your job is to figure out which one of those alkyl halides can be transformed into a Grignard, or excuse me, a Wittig reagent that would make that alkene. So A is the correct answer. So how did we arrive at that? So looking at that part in blue, how many carbons are there? 1, 2, 3. So we need a propane derivative. the new bond has formed at position 2. So 2-iodopropane reacted with triphenylphosphine. Gives that salt. We can then deprotonate. So that's going to make the ylide. And then that'll undergo the Wittig reaction. So when you're looking at these targets, try to map things out, whether you use it with colors or highlighting or numbering, to look at the main functional group, which is an alkene. How does the Wittig reaction dissect that? So for example, on here, we made that alkene one way. We could look at a different pair or couple. So if we wanted to reverse things, we could say that that top could come from the ketone, and then the bottom part could come from that Wittig reagent. So the choice of carrying that out in lab in real time, again, would be dependent upon the cost of those starting materials. What's the ease of handling them? For the most part, during lab work, you want to start with things that are solids. If they're not solid, then a liquid is preferable. The least preferable thing, is an oil and then a gas. They get increasingly more difficult to handle when you're thinking about measuring things out. Any questions on the Wittig? So Wittig will take, again, a carbonyl to an alkene, and you can do that two ways. So moving forward, now we're going to get into some things that will allow us to take oxidation state 2 functional groups, aldehydes or ketones, up an oxidation state. Before we get into those reactions, we have to orient ourselves along the carbon backbone relative to the carbonyl group. So in these two molecules, we have pentane, and then we have 2-pentanone. In pentane, all of the carbons are sp3 hybridized, and so every CH bond is a weak acid. So the pKs are about 45 to 50. When we do a substitution, so say on this carbon, we put that carbonyl. What ends up happening, the adjacent carbons, even though they're still sp3 hybridized, the acidity drops quite a bit. And so that's reflected down here in this table, depending on what what else is sort of bonded to those carbons. So you're essentially making it 10 to the 25 times more acidic. And when we refer to those specific carbons or groups, if it's a carbon, we call it an alpha carbon. And in this case, because there's a methyl and a methylene, we can say alpha and alpha prime, however we want to differentiate them. So based on what this R1 group is, there's your different functional groups. If R1 is a heteroatom, again, that's when we go up in oxidation state. So of the carbonyl containing functional groups, we have aldehyde, carboxylic acid, ester, anhydride, amide, acid chloride. And the reason I grouped these all together is that there's only one alpha carbon, because that other thing that's bonded is not a carbon atom. So in a sense, these can all be lumped together. So again, that hydrogen that is more acidic is highlighted in blue. The issue really comes with ketones, because you have two alpha carbons. And there is when you have a choice. So of ketones, remember there were two types. Symmetric ketones, where both groups bonded to the carbonyl are the same thing. So in essence, the alpha carbons kind of reduce due to symmetry. But ketones that are not symmetric will have these scenarios of alpha and alpha prime. And then I want to draw one more line here, right here. The alpha carbons that I circled in red, notice that those carbons do not have H's attached to them. So in essence, what the non-symmetric, with one side having no hydrogens, renders the other side the only reactive site. So it's these ones where alpha and alpha prime both have hydrogens and are different that a lot of the complexity arises from. So we're going to revisit that quite a bit in the next module, but knowing these differences now is going to help us learn the next reaction that's coming up. So this is still an addition reaction, and it's called the Baeyer-Villiger oxidation. For the first example shown, we're going to start with an aldehyde. And remember, there's only one alpha carbon. When an aldehyde is treated with MCPBA, we've seen that reagent a couple times. The structure is shown below. This oxygen in blue here, that baby blue oxygen, it is inserted into that CH bond. So once it's inserted, look at how the oxidation state of the carbon changes. So we start with an aldehyde at 2. We've made an acid, so we've gone up in oxidation state. Then the byproduct of this is the stuff left over from the MCPBA. So one of the things that maybe eases the mental burden of this is anytime you start with an aldehyde, with a Baeyer-Villiger reaction, you always get a carboxylic acid. The oxygen always inserts between that C and that H. And as I mentioned a couple minutes ago, where it gets difficult is when you have ketones. If the ketone's not symmetric, where does the oxygen insert? So let's, before we get to that, see how some arrows are pushed for this. And I'm just going to call the rest of the MCPBA R1, so I don't have to write it out a million times. So the first thing we want to do, because we're starting with an acid, is use the electrons on the carbonyl group as a base. So we've seen that before where we activate the carbonyl. So we'll balance off that plus charge now with this minus charge. For this species, I'm just going to draw a resonance form so we can see why the oxygen attacks where it does. So a resonance form would make the oxygen here neutral, and then that carbon plus. So we have O minus, C plus, we'll have that attack that carbon. So overall, the carbon atom is still at oxidation state 2. We need to bring it up. And so to do that, we're going to show kind of an elimination and then a migration. If those electrons collapse. That's going to form a pi bond. And then we're going to have the electrons in this CH sigma bond move over. So it's going to attack that oxygen. And then once it does that, we can break this OO sigma bond. And then one last acid-base reaction. To get our desired carboxylic acid and then the byproduct of MCPBA. With an aldehyde, again, you'll always end up with a carboxylic acid. See this step right here, the migration? This is where it gets complicated when you have a ketone, because that group is going to be carbon. If you have two different carbon groups, which one then undergoes the migration? If the ketone is symmetric, it won't matter which group. So the non-symmetric ones are going to be the ones we have to use a trend to establish which group is going to migrate. Regardless of that, if you start with a ketone, you end up with an ester. So it's still oxidation state 2 to 3. So we have a symmetric ketone. It's a 4-carbon chain, and then the ketone's at the 4 position. So when we look, alpha and alpha are the same. And then what I've shown here is our ketone oxidation state of 2, the alpha carbon is 0. That oxygen atom of the MCPBA is going to insert between the carbonyl and alpha carbons. So when it does that, we end up with an ester. And then look at how the oxidation states have changed. This is now 3. The carbon formerly known as alpha carbon is now 1. So for a symmetric ketone, it doesn't matter which side the oxygen inserts on, you'll get the same product. But when it's non-symmetric, we have to evaluate those alpha carbons according to a trend. So that trend is called migratory aptitude. And so you're basically examining each alpha carbon, and then aside from its bond to the carbonyl, how many other carbons are attached to it? And then you can classify it. So tertiaries will migrate faster than secondaries or aromatics, followed by primary, and then methyl is the least fast or the slowest to migrate. So now look at this ketone that's not symmetric and see if you can figure out which will be the major product. It's going to be A. So A and D are the two valid choices because they're both esters. B has some bullshit going on here where you have this weird oxygen, so that's not relevant. The issue with C, notice that oxidation state hasn't changed. So between A and D, how do we differentiate? So I'll call that alpha and that alpha prime. So when we look at this alpha carbon, we're going to ignore this bond to the carbonyl because it's shared by both. And then from that, we're just counting. So that carbon has 1, 2 carbons, so it's secondary. Then the alpha prime, we're ignoring the bond to the carbonyl. And so this one has 1, 2, 3, so that's tertiary. So the tertiary is going to be the one that is preferred to migrate, meaning that the oxygen inserts into that CC bond. Any questions? So for this one, really what you want to do is when you're given the ketone starting material, just classify and then use this migratory aptitude trend to determine where it's going to insert. So you can also run this reaction with cyclic ketones. Remember from way back when, you can't have a cyclic aldehyde where the C and the H are in a ring. You can have a ring as a side chain, but so for a cyclic ketone, we're starting with a 4-membered ring. And because we're inserting an atom, the ring size has to expand. So 4 goes to 5. And then we end up with a cyclic ester, and these are called lactones. So some common nomenclature for lactone ring size uses the Greek alphabet, where you're marking starting from the alpha and then just continuing on. So this 5-membered ring is called a gamma lactone. Another thing I want to point out, so since this is a symmetric ketone, we saw originally that those alpha carbons were more acidic due to the carbonyl. This carbon down here, this beta carbon, is not acidic. It's only the alpha carbons. You have two of them. When you run this reaction, notice what happens now. This former alpha carbon is becoming a gamma carbon. So really what it's doing is just leaving you with the one acidic methylene group. The beta and gamma are no longer acidic at all. So in a way, it's helping resolve things so that if you want to run further reactions, you're not going to produce a lot of undesired byproducts. So that gets us into now these oxidation state 3. So as we move forward in learning the reactions of those functional groups, I'm going to abbreviate the general structure as shown in the middle here. So there's our carbonyl, and then this X group has to be a heteroatom, because then that allows us to get up to 3. So the sp2 hybridized carbon X bond, anything sort of to the left of that includes the carbonyl is called an acyl group. So whatever all this stuff is. And then depending on what X is, that's how you get your different functional groups. So if it's chlorine, it's an acid chloride. If it's another carbonyl, that's an anhydride. If it's oxygen with carbon, that's an ester. Nitrogen, there can be amides, primary, secondary, tertiary. And I included this one as well, even though it doesn't have a carbonyl, the nitrile, because it's functionally equivalent. So as we expand off from these functional group transformations, oxidizing an alcohol up to an aldehyde or ketone, doing the Baeyer-Villiger, we can now get into carboxylic acids or esters. This allows us to then be pretty flexible in how we approach the synthesis of a molecule. Last reaction that we'll look at today is how can we use a process similar to Baeyer-Villiger but end up with amides. So so we saw that we can make cyclic esters called lactones through the Baeyer-Villiger. And we can also make cyclic amides. These are called lactams. It's going to use kind of a conceptually similar thought process, but we're now kind of piecing together stuff that we've learned so far. And I've just focused on the symmetric cyclic cases because it's a little bit easier to run through. But the point is we're now increasing the oxidation state, and at the same time we're differentiating all these other carbons of the backbone. And that helps us focus reactivity, and that's going to tie ultimately into the next module. The next named reaction is called the Beckmann rearrangement. So this example, we're starting with a cyclic ketone, so cyclohexanone. The first thing we're going to do is form an imine, but a special kind of imine. This is called an oxime. So we know a CN double bond is an imine, but that group up here is OH, so an alcohol. So that functionality is called an oxime. And that starts from hydroxylamine. So if we took ammonia, substituted an H for an OH, that's hydroxylamine. And that's the condensations that we learned in the last couple lectures. So if we look at, maybe I'll highlight it here. So this stuff has all the elements we need to make an amide, but the connectivity is not an amide. So as drawn, that's the oxime. But we can take the oxime and make an amide out of it. And so the Beckmann rearrangement will do that. So oxime to cyclic amide. Again, that's called a lactam. In this particular case, since it's a cyclic ketone, we have a 6-membered ring that's being expanded into a 7 while making the amide. So how do we get, that nitrogen atom into a ring, and then how do we get that oxygen bonded to the carbon backbone? And I just want to write these numbers in here. So oxidation state 2 to oxidation state 3. So in the reductive amination, we showed our imine nitrogen being protonated. So acid-base reactions in general are fairly fast. So they're reversible. We can protonate that nitrogen, but it can come back off. So protonating the nitrogen is not going to be productive for this mechanism. So the other heteroatom here is that oxygen. So let's protonate that. And I'm just going to abbreviate sulfuric acid as H plus A minus. So we know that sulfuric acid there's always a little bit of water present that we need to invoke as well. So now we have something that can be a good leaving group, water. And so at this point, one of these alpha carbons is going to migrate. So I'm going to choose this one and have this bond migrate from C to N. And when it does that, water is going to go away. I'm going to draw this a little weird so that you can see what's happening. When that bond migrates, the plus charge has to go somewhere. And because we broke a bond to this carbon, the plus charge has to go on it. And that's strange because the plus charge in an sp2 hybrid orbital, because we already have the p orbitals tied up in a pi bond, so this is pretty reactive. And so I'm just going to unfurl it into the 7-membered ring. This is going to allow us to use water as the oxygen source to trap that. We'll have that conjugate base do a proton transfer. So there's the acid. And so that sort of looks like an amide, but it's not quite an amide yet. And so the next thing that happens is not resonance, but tautomerization. So that's a special word because this H is going to migrate to that N. And so of these two forms, the amide is preferred, where we have the double bond between the carbon and oxygen, and then the hydrogen is bonded to the nitrogen. So because, again, the hydrogen's moving, these are called tautomers. And of those two forms, the amide is the one that's preferred based on comparing the pi bonds, whether it's CN versus CO, and then the H bonds, whether it's bonded to oxygen or nitrogen. And so through that, again, we've expanded that ring size to 7, and then we've increased that oxidation state. So what we'll continue on Wednesday and then Monday is looking at all the reactions of these functional groups now. What can we do with them? What are their spectroscopic signatures? And I think your next exam would be, I think, Monday. So